In today's video, we are going to learn about resonance. Look at the picture. The man pushes the swing at regular interval of time. If he does not apply the force in regular interval of time, then the swing may not gain the momentum required. Hence, he applies periodic force because of which the swing gains momentum and gains energy. So, he needs to apply the force in such a way that it increases the amplitude of the swing. This is the main logic of understanding what resonance actually is. Now let's understand it in a better way. Let's say there is an object which has its own natural frequency. There is an external periodic force which is applied on that object, and suppose if the external periodic force is equal to the natural frequency of that object, then there will be an increased amplitude in the vibration of that object. This increase in amplitude is called resonance. So let's see the definition of resonance. When the frequency of the externally applied periodic force on a body is equal to its natural frequency, the body readily begins to vibrate with an increased amplitude. This phenomenon is known as resonance. Let's see what are the conditions required for resonance. Let's say a force is applied on a body, and this applied force causes force vibration in the body, and the frequency of this applied force is exactly equal to the natural frequency of the body. Then the resonance occurs. At this point, a loud sound is heard because the body vibrating with a very large amplitude sends a large amount of energy. This is the demonstrations of resonance. Here we will be demonstrating resonance using tuning forks. Let's say there are two tuning forks. The tuning fork A and the tuning fork B. Both the tuning forks are mounted on top of sound boxes, and both the tuning forks have the same frequency. So when tuning fork A is struck by a piece of wood, it starts vibrating and sends the forced vibration to the sound box, and thus the air particles inside starts vibrating. These air particles send the vibration and energy towards the air particles in the box B. The forced vibration from the air particles in sound box B sends the vibration to tuning fork B, and tuning fork B starts vibrating by itself. This is because The air particles present in the sound boxes sends its energy to the air particles in the sound box B, and thus the tuning fork starts vibrating. This is because of resonance. Next, using pendulums. Let's say there are pendulums suspended over rubber string. Here, the length of the pendulum, if you see, looking at the pendulum X, the pendulum X and pendulum C has the same length, whereas the pendulum A, B, D and E are of different lengths. Shorter the length of the pendulum, higher will be the frequency, and longer the length, lower will be the frequency. But if the length of the pendulums are same, then the frequency also remains same. First, pendulum X is set into vibration by displacing its bob to one side normal to the length of the string. Pendulum C also starts vibrating initially with a small amplitude, and gradually it acquires the same amplitude as pendulum X. When the amplitude of pendulum C becomes maximum, the amplitude of pendulum X becomes minimum because of sharing of energy by them. Thus, the amplitude of pendulum C decreases and that of X increases. This process continues until and unless the resistance in air damps the force and they come to stop. The pendulum C starts vibrating because the natural frequency of pendulum C is equal to that of X, as they are of the same length. And therefore, there is an exchange of energy between the pendulum X and pendulum C. This again shows how resonance affects the movement or the vibration of the pendulums with the same length. Next, we have resonance in air column. Look at the picture. There is a tuning fork which is attached on the stand, and also there is a pipe which contains water, and this water is again connected by a reservoir at the different stand. When this reservoir is moved up and down, the water column over here gets increased or decreased respectively. When the water column increases, the air column on top decreases, and when the water column decreases down, the air column above increases. Here, natural frequency of air is inversely proportional to the length of air column. Sorry, there's a mistake out here. Of natural frequency of air is inversely proportional to the length of air column. This means that if the air column is very small, suppose if the water is up till this point, then the air column will be only this much. That means the frequency of the air column will be very high. But if the air column is increased, the water is up till here, and compared to the air column the previously mentioned, if the air column is increased from here to here, then the frequency of the air column decreases. As the air column increases, the frequency decreases, and as the air column decreases, the frequency increases. So, more the length, less will be the frequency, and less the length, more will be the frequency. Now, the vibrating tuning fork is held just above the mouth of the tube, and it produces forced vibration in the air column out here. When the frequency of air column is decreased by increasing the length of air column, when this air column is increased at a certain level, let's say at this point, a loud sound is heard. So when the loud sound is heard, this happens because the natural frequency of air column becomes equal to the frequency of the tuning fork. That is the case of resonance, and the vibrations of air column are in resonance with those of the tuning fork. If this air column is increased, or if the water level goes down, the frequency of air column does not remain equal to the frequency of the tuning fork. So the loud sound that was produced now stops. But on further lowering the level of water at a certain time, again the loud sound may be heard. This again is because the frequency of air column again becomes equal to the frequency of the tuning fork when the length of air column becomes 3 times the previous length or 5 times the previous length. So the resonance may occur again. This means that if initially the loud sound was heard when the air column was 10 centimeters, again next time the loud sound will be heard when the air column becomes 30 centimeter and 50 centimeters each. Next, some examples of resonance. Soldiers are asked to break their steps while marching while crossing a suspension bridge. When troops crosses the suspension bridge, the soldiers are asked to break their steps. The reason is, when soldiers march in steps, each soldier exert a periodic force in the same phase, and thus the bridge executes the forced vibration of frequency which is equal to the frequency of the steps. Now, if the frequency of the steps become equal to the natural frequency of the bridge will vibrate with a large amplitude, and thus the suspension bridge may collapse. So here is a picture how the bridge may swing and eventually it may collapse. Second example is, if some sound is produced with the same frequency as the frequency of any glass, and if the frequency matches with the natural frequency of the glass, then the glass may break. You may have heard when some singers sing, it's not loud enough they are singing. If they sing at certain frequency, the glass can break. This is how actually it may seem like. Resonance in radio and television. While tuning the radio or tuning the television set, they are required to be tuned in such a way that their frequency matches the frequency of. When the frequency of the signal becomes equal to the frequency of the TV or radio, then the signal is amplified because of resonance. This amplified signal is again used for broadcasting the TV or radio programs. So with this we come to an end of our video. I hope you have understood the concept and you have liked the video. Thank you.